seems like you didn't start live streaming from Zoom yet.
But Zoom says we are live.
Okay, I will do this again.
Oh, okay, right.
No, I just started again. You can tell this to Girai, I guess.
So Hassan just restarted the live stream from Zoom. So
yeah, it's live now.
It's live now?
Yeah.
But
I can't see Hassan yet.
Yeah, but on YouTube, it's still like waiting for Onur Mutlu lectures.
You're switching the CLR-DRAM on, right? Because I see that.
This one, right?
I see. Could you refresh? Sometimes you have to refresh.
Okay.
Okay.
Thanks. Yeah.
I guess we can get started now. So this is the fourth meeting of PNS Ramulator, and today we will start with covering this paper called CLR-DRAM. This paper presents a mechanism on improving DRAM performance, and in the second part of the meeting, we will go over the project updates, which will be off YouTube live stream. Okay, so Hasan will present this CLR-DRAM paper. So Hasan, please start when you're ready.
Okay, thanks, Hassan. So hello, everyone. Today I'll be presenting CLR-DRAM, a low-cost DRAM architecture that enables a dynamic capacity latency trade-off. This work is motivated by the fact that workloads and systems have varying memory capacity and latency demands. However, commodity DRAM, as the prevailing technology for the main memory, makes a static capacity latency trade-off at design time. As a result, commodity DRAM could not adapt to changes in the workloads and systems' memory capacity and latency demands. Our goal in the paper is to enable a dynamic capacity latency trade-off in DRAM at a fine granularity, that is, a single DRAM row to meet the changing capacity and latency demands of the workloads. To this end, we propose CLR-DRAM, standing for Capacity Latency Reconfigurable DRAM. CLR-DRAM is capable of dynamically reconfiguring a single DRAM row to operate in either a max capacity mode with high storage density or a high performance mode that can operate with low access latency and low DRAM refresh overhead. The key mechanism of CLR-DRAM consists of two techniques. First, we couple two adjacent DRAM cells in a row and their two sense amplifiers to operate as a single high-performance logical cell. Second, we can dynamically turn on and off such coupling to switch between the two modes. Our SPI simulation shows that a high-performance row in CLR-DRAM significantly reduces four major DRAM cell access timing parameters. Our system-level evaluation shows that mapping pages to high-performance mode rows in CLR-DRAM improves average performance and saves DRAM energy. Here's the outline of the talk. The long access latency of DRAM is a performance bottleneck. However, it's not intrinsic to the DRAM technology itself. There's a fundamental trade-off between storage capacity and access latency in DRAM, and commodity DRAM overwhelmingly favors storage capacity at the expense of access latency. The figure on the right, which is taken from tiered latency DRAM, illustrates how latency and storage capacity affect each other in the conventional DRAM architecture. Modern workloads have different main memory capacity and latency demands. Existing systems miss the opportunities to improve performance by adapting to these changes in main memory capacity and latency demands. The memory capacity of a system is usually over-provisioned, while many modern workloads tend to underutilize the system's memory capacity. However, commodity I'm sorry. Once manufactured commodity DRAM are either capacity optimized at the cost of long latency or latency optimized at the cost of small storage capacity. Even some state-of-the-art heterogeneous DRAM architectures employ only a fixed size and small low latency region, which does not always provide the best possible operating point within the DRAM capacity latency trade-off spectrum for all the workloads. As a result, commodity DRAM could not adapt flexibly to the changes in the system's memory capacity and latency demands. Therefore, in this paper, our goal is to enable a dynamic DRAM capacity latency trade-off at a fine granularity, that is, a single DRAM row, as shown pictorially in this figure. Next, I will briefly introduce how DRAM works. A DRAM chip contains multiple independent DRAM banks, each consisting of multiple subarrays of DRAM cells. A DRAM cell stores one bit of data using electric charge level. A typical density optimized DRAM subarray architecture is shown on the right. To access data stored in the DRAM cells, the memory controller issues an activate command to activate a row of DRAM cells. Oops. The electric charge in the cells are then sensed and read by DRAM sense amplifiers, placed on both sides on the subarrays through bit lines. This kind of array architecture is called open bitline architecture. The sense amplifiers operates in a differential manner. It reads data stored in the cell by sensing and amplifying the voltage difference across a pair of bit lines caused by the charge sharing between a DRAM cell and the bit line when a row is activated. During activation, another bit line in a neighboring subarray is also involved to serve as the reference of the sense amplifier. Here we show the procedure of accessing a fully charged DRAM cell. The x-axis is the time and the y-axis accesses the voltage levels in the cell and the bit lines. The activate command let the DRAM cell share its charge with a bit line. This generates a voltage difference across the bit line pair. When the difference is large enough, the sense amplifiers start to amplify this difference and enters the charge restoration process. During charge restoration, when the voltage difference is large enough, we can safely issue a read or write command to the DRAM row. The latency between an activate command and the earliest possible read or write command is called TRCD. At the same time, the charge restoration process continues to restore the charge level back to the cell. The latency of fully restoring a DRAM cell is called TRES. After TRES, the row can be safely closed. The memory controller issues a precharge command taking TRP amount of time to close the row. Cells have to be periodically refreshed to ensure data integrity. Now I will introduce our new design, CLR-DRAM, capacity latency reconfigurable DRAM. CLR-DRAM is a low-cost DRAM architecture that enables a single DRAM row to dynamically switch between either max capacity or high performance mode. The key idea of CLR-DRAM is to enable dynamic configurability of the connections between DRAM cells and the sense amplifiers in the density optimized open bitline architecture, which is shown on the left. To do so, CLR-DRAM, which is shown on the right, adds two types of isolation transistors. We call them type 1 and type 2 bitline mode select transistors to enhance the connectivity between the DRAM cells and the sense amplifiers. For a row to operate in max capacity mode, CLR-DRAM enables type 1 transistors and disables type 2 bitline mode select transistors to mimic exactly the same cell to sense amplifier connections as in the open bitline architecture. Doing so enables every single DRAM cell and its sense amplifier in a max capacity row to operate individually, and thus achieving the same storage capacity as a row in the conventional density optimized open bitline architecture. For a row to operate in high performance mode, CLR-DRAM enables both types of bitline mode select transistors to enable two kinds of coupled operations simultaneously. First, two adjacent DRAM cells in a row are coupled to operate as a single logical cell because they are connected to both ports of the same sense amplifier. Second, these two sense amplifiers, which originally served the two adjacent cells individually, are now coupled to operate as a single logical cell sense amplifier because the logical cell is connected to both of the two sense amplifiers. A high-performance mode row has reduced access latency and refresh overhead via these coupled cell and sense amplifier operations. Next, I will explain how could the coupled operations in high-performance mode reduce access latency and refresh overhead. I will start by describing what coupling two cells and two sense amplifiers enables. A logical cell always stores opposite charge levels in the two coupled cells to represent the same bit of data. This is because the sense amplifier always drives the two bit lines that each of the coupled cells is connected to into complementary voltage levels respectively. This property of a logical cell enables three benefits. First, it reduces the latency of charge sharing. Second, it enables early termination of charge restoration. Third, it enables retaining data stored in the logical cell for a longer period of time. A logical sense amplifier operates faster by having two sense amplifiers essentially driving the same logical cell. This also enables three benefits: the reduction in the latency of charge restoration, precharge, and refresh. And now let me explain how operating with a logical cell and a logical sense amplifier reduces DRAM access latency. As a recap, the coupled operation of two cells and two sense amplifiers reduces DRAM latency in three ways. These three ways of latency reduction altogether reduces the activation, restoration, and precharge latencies of a high-performance mode row in CLR-DRAM. The opposite charge level stored in the logical cell reduces the charge sharing latency by driving both bit lines of the sense amplifier into opposite directions during charge sharing. It reduces charge sharing latency because the voltage difference across the two bit lines reaches the threshold voltage required by the differential operation of the sense amplifier earlier than the baseline case, where only one DRAM cell is involved during charge sharing. The opposite charge level stored in the logical cell also enables a high-performance mode row in CLR-DRAM to terminate its charge restoration process early. We make two observations about charge restoration. First, charge restoration process has a long tail latency. Our motivational SPI simulation shows that it takes about half of the charge restoration time to fully restore the last 25% of charge in the charge cell. This means that if we terminate the charge restoration process earlier, the charge level restored in the cell does not degrade significantly. Second, a discharge cell restores much faster than a charged one. This is because the restoration current of a charging cell is limited more than that of a discharging cell. In other words, if we terminate the charge restoration process of a logical cell earlier, we can still have the discharge cell fully restored. Leveraging these observations, we reduce TRAS by terminating the charge restoration process early. Our SPI simulation shows that TRAS could be significantly reduced with only a marginal negative impact on TRCD, which is due to the reduced charge level in the cell just prior to the activation. The logical sense amplifier reduces the charge restoration latency simply by having two physical sense amplifiers driving the same logical cell from both ends of the bit lines. This largely offsets the long latency caused by long bit lines in the density optimized open bitline architecture. The precharge latency is also reduced because two precharge units, which are associated with the sense amplifier, are also coupled to precharge the bit lines together. As a result, by having the coupled operation of two DRAM cells as a single logical cell and two coupled sense amplifiers operating as a single logical sense amplifier, CLR-DRAM reduces the activation, restoration, and precharge latencies. Now let me explain how CLR-DRAM mitigates DRAM refresh overhead in high performance mode. CLR-DRAM reduces DRAM refresh overhead of high performance mode row in two different ways. First, it reduces the latency of a refresh operation. This is because since refresh a row is essentially restoring the charge level back to the cells and then perform a precharge to close the row. And the activation, restoration, and precharge latency reductions can also apply here to reduce the latency of a refresh operation. Second, since a logical cell contains two physical DRAM cells, it has a larger effective capacitance to tolerate more leakage. Therefore, less refresh operation is needed for high performance rows. We conclude that CLR-DRAM could reduce both the refresh latency and the refresh rate for rows operating in high performance mode. Let me move on to the evaluation part. First, we evaluate the latency impact of CLR-DRAM using SPICE simulation. We model a CLR-DRAM subarray based on the previously published technology parameters. We scale these parameters to match with recent technology nodes. And we have made our models public on GitHub. Our SPICE simulation shows that by operating in high performance mode, we can reduce major DRAM access latencies, TRES, TRCD, TRP, and TWR by 35.2% to 64.2%. We conclude that CLR-DRAM significantly reduces DRAM latency. Next, we evaluate the system level performance and DRAM energy impact of CLR-DRAM. We use Ramulator, a cycle level DRAM simulator, to evaluate the system level performance of CLR-DRAM. We analyze 41 real single core workloads from benchmark suites, 30 synthetic random and string access workloads, and 90 randomly chosen multi-programmed 4-core workloads. We model 5 configurations of CLR-DRAM. Each configures a different portion of all the DRAM rows to operate in high performance mode. For each configuration, we also map the same portion of the most access pages of the workloads to be placed in those high performance mode rows. First, I will start with the performance impact of CLR-DRAM. For real single core workloads, CLR-DRAM provide an average speedup of 12.4% when all pages map to high performance mode rows. For the 90 multi-core workloads, mapping all pages to high performance mode rows provides an average of 18.6% speedup. We observe that in all cases, the performance improvement increases when we increase the number of pages that are mapped to high performance mode rows. For the configuration that all rows are configured to operate in max capacity mode, CLR-DRAM can still achieve a small performance impact, mainly because of the significantly reduced precharge latency of coupling two precharge units. We conclude that CLR-DRAM improves system performance for both single and multi-core workloads. Next, we evaluate the DRAM energy consumption of CLR-DRAM. Mapping pages to high performance mode rows could yield an average of 19.7% DRAM energy savings for single core workloads and 29.7% for multi-core workloads. We conclude that CLR-DRAM saves DRAM energy. High performance mode rows in CLR-DRAM could mitigate the DRAM refresh overhead by both reducing the DRAM refresh latency, TRFC, and the DRAM refresh rate, which is increasing TREFW. First, we observe that only reducing the refresh latency in CLR-DRAM already saves DRAM refresh energy by 66.1% on average for multi-core workloads. If the refresh rate is also reduced by 3x, which our SPICE simulation shows is possible, we could further save DRAM refresh energy by 87.1%. And doing so still gives us an average speedup of 17.88% for 4-core workloads. We conservatively estimate CLR-DRAM to have a modest DRAM chip area overhead of 3.2%. Configuring rows to high performance mode incurs memory capacity overhead. However, due to the flexible reconfigurability of CLR-DRAM, the user is free to find and dynamically determine a favorable operating point in the DRAM capacity latency trade-off spectrum. We have more detailed discussions in a paper. We conclude that CLR-DRAM is a low-cost DRAM architecture. We also have a more detailed sensitivity analysis on the trade-off between reducing refresh rate and increased activation and restoration latencies, as well as its system-level impact in the paper. Our paper also includes some design details that makes CLR-DRAM work efficiently. Now let me conclude my talk. We propose CLR-DRAM, which stands for Capacity Latency Reconfigurable DRAM. This is a new DRAM architecture that enables dynamic fine-grained reconfigurability between high capacity and low latency DRAM operation. CLR-DRAM can dynamically reconfigure every single DRAM row to operate in either a max capacity mode that maintains almost the same storage density as the baseline density optimized open bitline architecture by letting each DRAM cell operate separately, or a high performance mode that provides low access latency and low refresh overhead by coupling every two adjacent DRAM cells in the row and their two sense amplifiers. Our evaluations show that CLR-DRAM significantly reduces 4 key DRAM timing parameters, improves systems performance, and saves DRAM energy. We hope that future work can exploit CLR-DRAM to develop more flexible systems that can adapt to the diverse and dynamically changing DRAM capacity and latency demands of the workloads. Yeah, thank you for listening to my talk. For more details, I invite you to take a look at our ISCA paper.
Hey, great. Thanks for the presentation, Hassan. Are there any questions? Okay, then. So let's continue the second part of